Okay, so shall we start? Yes, okay. So it's a pleasure for me to introduce today's talk on the European Non-Associative Algebra Seminar. The speaker today will be Yulia Zaitseva from HSE University in Russia, and she will talk about derivations on toric and trinomial algebras. So whenever you want, Yulia, you can start.
Thank you a lot for the opportunity to give me a talk here. I will give some survey about toric algebras and trinomial algebras, about locally important derivations on them, and connections to algebraic geometry, to actions of unipotent one-parameter subgroups, and to action of those. It is a short one. Let me start with the first item about GA actions and locally nilpotent derivations. I will talk about algebraically closed field of characteristic 0, and let me recall that a derivation on an commutative associative algebra R is a linear map that satisfies the Leibniz rule. We will call such derivation locally nilpotent if any element of an algebra is annihilated by some power of this derivation. For example, let R be a polynomial algebra in two variables. Then the partial derivative in X is locally nilpotent because any f has some degree in X, and if I will take this derivation some number of times, then I will obtain 0. The same thing is going with y multiplied by partial derivative in X, because the degree of y may increase, but the degree in X decreases, and at some moment the polynomial, any polynomial, becomes 0. But for example, X multiplied, if we will change y to X, then it will be not a locally nilpotent derivation, because if we take X, then we will obtain X, and then obtain X, and then obtain X, and so on, and it will nothing, it will be not 0 for any n. Okay. These locally nilpotent derivations have many wonderful properties. If you will not like my talk, you can think about the following exercise. For example, I have an LND on a commutative associative domain R, and let delta of f is divisible by f. Prove that delta of f equals 0. It seems like an easy exercise, but in fact, it is a bit tricky. Okay, let me recall some notions from affine algebraic geometry. By AN, I will denote the affine space. And let us fix some polynomials in n variables. Then an affine algebraic variety is a set of common zeros of these polynomials. It's written here. So we write a system of polynomial equations and consider its solutions. Such sets are called affine algebraic varieties. For any affine algebraic variety, we can consider the set of functions on this affine algebraic variety. We consider polynomials and restrict them to our x. For example, if we take x equal to that affine space, then the algebra of regular functions is just a polynomial ring. Why we do interest in locally nilpotent derivations? Because locally nilpotent derivations have close connections to the actions of such a simple one-parameter additive group of our ground field K. We have a bijection between locally nilpotent derivations on algebra of regular functions on X and GA actions on X. So we have some connections between geometry and algebra. To construct these connections, we use the exponential map. Let me give an example. Let X be an affine plane, and we know that its algebra of regular functions is a polynomial algebra in two variables. And let us consider two locally nilpotent derivations from the previous slide. Let us take exponential. Alpha is a constant from the field K. And let us apply this exponent to coordinates, to X and to Y. For X, we obtain X plus alpha plus 0 plus 0 plus 0, and for Y, we obtain just Y. And this gives us an action of the group J. If we act by a point with coordinates X and Y, we obtain such X plus Y, X plus alpha Y. So this is a equation with orbits that are parallel lines. If we change our locally nilpotent derivations to this one, then here we will add one Y, and the action will have this formula. And it is similar to this one, but here almost all orbits align, but one line consists of stable points, so it is some other actions. If you have any questions, please ask me at any moment. This was G actions and locally nilpotent derivations. And now let us speak a bit about tori. I think that the definition is well known. A grading on an algebra is a decomposition of this algebra in a sum of subspaces, and we want this condition to call it a grading. Let us denote by Gn the multiplicative group of the ground field K, and let X be some affine algebraic variety with some algebra of regular functions. Let us denote by T an algebraic torus that is the product of such multiplicative group of the ground field in some number, like let us denote it by R. And actions of torus are connected to gradings on an algebra of regular functions. So we once again have a connection between geometry and algebra. Indeed, any action of a torus T gives us a grading of an algebra of regular functions. It is similar to the decomposition of vector to the sum of eigenvectors when we have one linear operator which is diagonalizable. Any such component consists of functions that are multiplied by some number when we act by a torus T. What is this number? It is a character, so let us denote by M the lattice of all algebraic homomorphisms from T to GM, they are all of the following form. We obtain a tuple and take some monomial. These mi's are integer numbers, negative also. And one can prove that if you have any such action, then you have such a decomposition. And in another direction also. Let us mix two of these things. We already know that GA actions are connected to LNDs and torus actions are connected to gradings. And if we have both a grading and locally unipotent and some derivation, not necessarily locally unipotent, then we say that it is homogeneous if it sends homogeneous elements to homogeneous ones. One can prove that in this case, all elements shift by the same element of the group K, which is called the degree of the derivation dated. Okay, finally, let me write that if I have an affine algebraic variety and an action of torus T, then GA actions that are normalized by a torus T geometric condition are in one-to-one correspondence with homogeneous locally unipotent derivations on the algebra of regular functions. So geometric objects and algebraic objects. What does it mean normalized? It means that I take an action, depends on a parameter, and it is an element of the automorphism group of X. And if I conjugate it inside the automorphism group, then I obtain the element of the same form, but with some other parameter, and it appears that this parameter can be only multiplied by some character, and locally unipotent derivations that we obtain here will be of the same degree m as the character. So these m that appear as a degree of some locally unipotent derivations on Kx, they play a big role in the description of the automorphism group of this X, and they are called dimensional roots of the variety X, and the corresponding subgroups in the automorphism groups are called root subgroups. And a big problem is to describe these objects, describe for some given X and the torus action on X all possible homogeneous locally unipotent derivations or all possible dimensional roots. This is connected to the description of the automorphism group. I will not say a lot of details here because I have introduced only affine algebraic varieties, but in some other situation, this may describe all elements in automorphism group, because it's known that linear algebraic groups are generated by its maximal tori and root GA subgroups. So if you understand what is your maximal tori and find all root subgroups, then you know a lot about your automorphism group. One interesting situation here is that you can consider algebraic varieties that have not so many automorphisms, like automorphism groups. Let us call an algebraic variety rigid if it admits no non-trivial GA action. And it is proved that in this case, the automorphisms group is a finite extension of a centralizer of this torus T. So it may be described. The next topic that I want to introduce is affine toric varieties. This is a class of varieties very well known, and an affine variety is called toric if it admits an action of a torus with an open orbit. An open orbit means that the complement to this orbit is closed, and closed these are subvarieties of X that are also given by some system of equations in X. So we should think about this like X is some weak variety, and open orbit is a very big orbit. It's dense in X because the complement is given by some equations and it has less dimension than X. So there cannot be two open orbits if I have generalizer. If X is irreducible, then there is only one open orbit, and all other orbits are closed of a smaller dimension. Okay, and this is a very interesting class of varieties because they have a combinatorial description in terms of affines or polyhedral cones if they are affine. And the problems we start to discuss is describing all GA actions on X that are normalized by the acting torus T. So it is the same that describing all homogeneous locally unipotent derivations on the algebra of regular functions on X. Are there some questions at this point? I will consider two cases. First, I will consider normal toric varieties, and after that, non-normal toric varieties and their generalizations. Let me introduce this combinatorial construction, how to obtain this algebra from a cone. The answer to this problem will look as follows. X corresponds to some strongly convex rational polyhedral cone. And then we will find some special elements in the character lattice of the torus T in terms of this sigma, this strongly convex cone, in terms of its ray effects. In fact, only rays are used. Okay. Let me try to introduce the construction. Consider the lattice M, which we already have seen here. It's the lattice of all possible algebraic homomorphisms from T to GM. Any such homomorphism is given by some element in the lattice because it is just taking a monomial. And let us also consider the set of all algebraic homomorphisms in other direction, from GM to T. They are also inside a lattice because it looks like T tends to some monomials in T n times. These lattices are dual, they have a pairing, and in coordinates it's just taking a scalar product, element from here and element from here. if you wish to think about this without coordinates, then you should take the composition of these two homomorphisms, and then you will obtain a homomorphism from GM to GM, and it has a form T is going to the T to some integer power, and this integer will be the result of the pairing. Let us consider some cone. Strongly convex means that there are no lines inside it. Rational means that we are working over a field of rational numbers. And it is such a linear span, but with non-Joule coefficients. Some elements that lie in the lattice. We can take these vectors primitive. So it's like we are taking some vectors and consider everything inside them. A dual cone is inside the vector space that is spanned not by n but by m, and we take all vectors that such that pairing is non-negative. So all vectors with acute angles with all the vectors inside the first cone. And then we intersect this cone with a lattice and in a same group. And then we can consider for any element of this same group such a formal sum of one-dimensional vector spaces, where we multiply chi m by chi m prime is equal to chi m plus m prime. And for such an algebra, there exists some algebraic variety with this algebra of regular functions. So we have how to construct from any strongly convex rational polyhedral cone an affine algebraic variety, and it appears to be toric, so it has a natural action of a torus on it. Torus has the same dimension as x and equals to n. This dimension equals to n. Let us consider an example. If I will take positive octant inside a first vector space, then due to it is also positive octant. If I will intersect it with a lattice, then I will obtain in this positive octant only integer points. And then I take a sum of all characters for m lying in my same group, and we see that it is just a polynomial ring. So here X is a affine space. If you will take some other cone here, then here you may obtain some conditions on x1, xn, and then it will be not the affine space, but some subvariety in this affine space. Okay. And now let me give an answer how to describe all local unipotent derivations on such algebras that are algebras over some cones. Yes. Let us call an element in the lattice of characters a de Mazur root of a toric variety if the following holds. I take one of primitive vectors on the race and take all such elements E that the pairing with one of them is -1, and the pairing with all others is at least 0. And let us consider an example. If I take, as in the previous example, an affine space and a positive octant, then primitive vectors are basis vectors. And one coordinate is -1, and all other coordinates are at least 0. So we have n such parts of hyperspaces that form a set of demesurhoods. The corresponding locally nilpotent derivation of degree E is given by the following formula. I can define my locally nilpotent derivation only on basis, and let me define it in the following way. It is some number, and chi m goes to chi m plus E multiplied by this number. And the theorem is that any homogeneous locally nilpotent derivation on a normal toric variety has such a form, may be multiplied by some constant. So we have a full description of locally nilpotent derivations that are homogeneous, and this gives the description of root subgroups in the automorphisms group of a normal toric variety. In our example, the derivation has the following form. One can see that it is indeed locally nilpotent because in this monomial there is no xi, and the degree of xi decreases, and this means that any polynomial will be annihilated by some power of this locally nilpotent derivation. Let me stop a bit on these conditions, why it works in the general case, why we obtain locally nilpotent derivation. Why any chi m will be annihilated by some power of this derivation. Because when we apply it many times, we obtain here m plus e, m plus 2e, m plus 3e, and e is chosen in such a way that it gives -1 with some ray of sigma. This means that this element m plus e is m plus e, m plus 2e, m plus 3e, and so on. They are closer and closer to some face of a dual cone because of this condition. And at some moment we come to the hyperface of this cone, and after that there are no points because all points in our algebra are inside this dual cone. And when we will reach the face, then we will obtain 0. In fact, we will obtain 0 here. Okay, if some questions, please ask me. Let us go to the case 2. It is a generalization of this normal case. We can construct non-normal toric varieties from affine subgroups. Let us, for example, consider natural numbers and 0 without 1. Then the algebra for such monoid will be the following. When we sum all monomials except x, then we have the following algebra, and this is an algebra of a variety given by an equation x1 cubed is equal to x2 squared in A2. It is a non-normal toric variety. And any non-normal toric variety is obtained in such a way. We have to choose some monoid inside a cone. Here we have to change definition of a de Mazur root to the following one. The first condition is the same, and for the second condition we have to ask that any such sum is inside S, because we have only functions chi m for m inside S. The formula for LND of degree is the same, like here. And the same theorem, any homogeneous element is described by these de Mazur roots. It was proved in this work. For example, we can see that here there are no de Mazur roots because of the second condition. The unique possible de Mazur root could be -1, but -1 is not a de Mazur root because -1 plus 2 is 1, which is not inside S. Okay, let me consider another class of algebras. With toric algebras we are done. And let me consider trinomial algebra. It looks a bit technical, but in fact, nothing scary is here. I will consider polynomials that are the sum of 3 monomials. And all these monomials have different variables. Let me denote them in this way. T0 something for the first monomial, T1 something for the second monomial, and so on. A trinomial hypersurface is a hypersurface given by one such equation that some trinomial equals to 0. And trinomial algebra is an algebra of regular functions of this hypersurface. It is just a quotient algebra by this trinomial. So let me say once again that we consider quotient algebras of a polynomial algebra by some sums of 3 monomials with different variables. And I would like to describe local nilpotent derivations on such algebras. But the description of local nilpotent derivations is too difficult. We consider homogeneous locally nilpotent derivations, since they correspond to root subgroups. So I need to introduce a grading. Let me introduce a grading. First, I will try to take some weights for all these variables. but it doesn't work because if I want to have a grading on a quotient algebra, then I need some conditions on these weights, and these are the following: that the degree of any monomial is the same, or degrees are equal. And when I will take this quotient group, then I can define the degrees of variables in this group. This will be a very well-defined grading, and we would like to describe all locally nilpotent derivations that are homogeneous with respect to this grading. This is the problem, and let us look at the answer. First, I will introduce some special class of derivations, and then it will appear that these are all possible ones. Before that, I would like to say a bit of motivation why we consider such trinomial polynomials. Because these trinomials are closely connected to torus actions as well. When we have an action of an algebraic group on an algebraic variety, then there is some typical dimension of orbit. So a dense subset of my variety consists of orbits of the same dimension. Let us call by the complexity of an action a codimension of such a typical orbit. For example, if I have an action of complexity 0, this means that codimension of my typical orbit is 0, or in other words, that I have an open orbit. And if I have such a torus action, then we have our previous case toric varieties. And one can prove that toric varieties are given by equations that are binomials. So they have one monomial plus another monomial equals 0. And if we consider actions of complexity 1, the next step, then one can prove that they are closely connected to trinomials. There are some technical details, but there is some very important invariant of X called its Cox ring. It is graded by a class group, and this Cox ring is a quotient algebra by deals generated by trinomials. So the same algebra that we are going to study. Okay, let me introduce some derivations on this algebra, a quotient algebra by some trinomial. Let me take 3 integer number and 3 number from my ground field that are 0 in the sum. Then I will consider the following cases. If all these numbers are not equal to 0, and there exists only one exponent in my trinomial, such that this exponent is at most 1, then I will take my locally nilpotent derivation delta c beta by the following formula. And if the following condition is true, then I can consider a derivation defined by this formula. I don't think that this looks nice, but in fact, if you will think about it for 1 minute, then you will see that they are really elementary, because there are many variables, but most of them are going to 0. And there are only 1-2 variables that are not going to 0, and they are going to something like this, but this is chosen just in the following way to obtain that delta sends our trinomial to 0. We need this condition to have a well-defined map on a quotient algebra. So these derivations are very natural. And also, if you have a local nilpotent derivation, then you can multiply it by an element from the kernel. Then it will also be a local nilpotent derivation. We consider only homogeneous elements. This delta is homogeneous. We multiply it by homogeneous and obtain more derivations that are called elementary derivations. Okay, and this gives us a description of all homogeneous local nilpotent derivations. It was proved in different works. In the first work for primitive local nilpotent derivations, I will not define this notion. And then in the general case, we can find a corollary of this theorem and find situations when there are no homogeneous local nilpotent derivations. If there are no homogeneous local nilpotent derivation, then it is just the case where let me better formulate, when it admits non-zero local nilpotent derivations. It admits local nilpotent derivations if there is some exponent equal to 1. And we can make a corollary from this corollary and find a criterion for rigidity for trinomial factorial hypersurface. It is the following: if and only if all exponents are at least 2. And this corollary was proved in this work. For example, such trinomial hypersurface in a affine 3-dimensional space is rigid. It admits no homogeneous local nilpotent derivations and no local nilpotent derivations at all. Let me give some extra examples. This is an example with some trinomial that admits some derivations. And it is easy to construct them from the construction on previous slides. We find a variable with exponent 1, and we can choose it and some other variable, this with this, or this with that. And this gives our 2 cases, A and B. We look at, for example, let us choose T01 and T21. Then they go to the partial derivations of these monomials by these chosen variables. So if I will take a partial derivative by T01, then I will obtain this thing. And if I will take here a derivation, then I will obtain to t to 1, and so on. And if we want, we can describe de-Mazur roots. So the degrees of these locally nilpotent derivations. Example 3 is a picture in some other case with all possible degrees. This is the picture. It consists of 4 such blue cones, integer points in these blue cones, and 4 layers with not all integer points inside these layers. Okay, let me also prove here something. I decided that we can prove some lemma, which I think is very easy on the one hand, but on the other hand, it proves a lot. Let delta be a locally nilpotent derivation on a trinomial algebra. And then I will prove that in this case, many variables are going to 0. So any monomial, any of our 3 monomial, contains at most 1 variable that goes to 0. That not goes to 0, and all other are going to 0. In the proof, I will use this fact that I formulated earlier. Okay, let me take the following grading on my algebra. 2 variables will have degrees some non-zero, and all other will have 0 degrees. L01 is the degree of T01, and the degree of T02 is the exponent was TLO2, so the first monomial will also have degree 0. Okay, and there are 2 possible cases. The degree of my delta may be positive or negative. And in both of these cases, we will obtain that sum of these 2 variables is going to 0, so they both cannot go to some non-zero element. Indeed, if the degree is positive, then the degree of the image is, by definition, the sum of degree delta and the sum of degree of this variable. And it is positive because this one is non-negative, and this one is positive, it is some exponent. Okay, but how can I obtain a positive degree? Only if I will include in any monomial this variable, because all other variables have either negative degree or 0 degree. So in any monomial of this element, I have T01. This means that delta of T01 is divisible by T01. And the general fact on locally nilpotent derivations says that in this case, the image is 0. The second case is very similar. Okay, here I would like to stop with simple case of trinomial algebras with this one. If you have any questions, please ask me.
Excuse me, is your last lemma saying that the intersection of kernel of all local nilpotent derivations is trivial?
No. For example, here, if we look at this example, yes, we have two types of homogeneous locally nilpotent derivations, such derivations or these derivations, but T1 is in the kernel of, not T1, well, let me find some element, for example, TO2, yes. TO2 is in the T02 in the kernel of both of them. So I don't say that the intersection of all derivations is trivial. It says another thing, that if I have one locally nilpotent derivation, then it is very similar to trivial. So it since let me look at my trinomial. This is a trinomial, and the lemma says that in one summand, I can have only one variable that is not in the kernel. So one variable can be not in the kernel, and all other are in the kernel. Or another option is that all of them are in the kernel. This is the statement of the lemma.
Yeah, thank you.
But this is this case that we have considered. Oh, there's one more question in chat. Is there an algorithm to check which variable is in the kernel? It depends on how generally there are some algorithms to check that polynomial is inside the kernel, and even there are some algorithms to find that try to find the kernel of a locally nilpotent derivation, find generators of the kernel. But I think that in our case, if I have so it depends on how it is given. If I have a locally nilpotent derivation that is given by that is elementary, yes, for trinomial algebra, then I just know which elements are going to what, and I can use exponents of my trinomial and see which of variables are going to 0 and which are going to a non-zero element. If I haven't answered, please ask me once again. Maybe I haven't understood the question.
He says it's okay, so you continue. You can continue.
Okay. So we are studied. I recall that we are studied trinomials because of this theorem. But here, an ideal is generated not by one trinomial. It is generated by trinomials in some special way. Let me introduce this special way. It will be a bit tricky, but here will be just many trinomials of this form. This is this slide. There are algebras of two types. One type is a bit easier, another type is a bit more general. And we have to fix something like some numbers. Sometimes we will start from 0, sometimes we will start from 1. Also, we have tuples, and also we have such monomials. And trinomial algebras of type 1 are given by several polynomials of the following form. two monomials and some number. AR are pairwise different numbers. Okay, and in type 2, I fix some pairwise linear independent columns from K2 and consider determinant of such a matrix. It is 3 by 3 because A1 are columns, and it is a trinomial. To 3 is this monomial with some coefficients that are coming from the determinant. And trinomial variety is a variety defined by all these trinomials. In type 1, all such trinomials, in type 2, all such trinomials. For example, SL2 is a trinomial variety of type 1, because we have one monomial minus other monomial, they have distinct variables, and minus some number. You can find such AI. Trinomial algebra is, as usual, a quotient algebra by all our polynomials. In the same way as in the simple case, there is a natural grading where we take firstly all degrees of variables different, and after that take a quotient by the conditions that all summands have the same degree. And the useful task is to describe homogeneous locally nilpotent derivations in that general case. And the answer is similar. There are also some elementary derivations. I added also here some variables without any conditions, free variables. You can take partial derivatives of them. Also, there are similar locally nilpotent derivations to the simple case that do not depend on any constant from the ground field, only from the choice of some exponents in our monomials. And there are also derivations of type 2 that depend on how much of elements are equal to 0. And we call all these derivations elementary, and also when we multiply them by some elements from the kernel that are homogeneous, they will be also called elementary. And it appears that any homogeneous locally nilpotent derivations can be found in these terms. So we also have a combinatorial description of roots in this case. Here is a corollary when we have no homogeneous locally nilpotent derivations with respect to this grading. This is not the same as rigidity, because rigidity is when we have no locally nilpotent derivations at all. And here we have a condition of homogeneous. But if we will delete the torsion part from our grading group, then the task will be the same. And here also is given a criterion of rigidity. First 3 conditions are the same as on the previous slide, and also these varieties are also not rigid. And I think that it's nice that we have some classes where we can find some concrete descriptions of all locally nilpotent derivations in some very concrete terms, because in some explicit terms, because generally the task is very difficult, and if we have some classes of examples, then we can test some theories on these classes, and I think it would be nice to find some more classes where we can describe all derivations and rules explicitly. Thank you for your attention. If you have some questions, I would be glad to answer.
Thank you very much, Julia. Is there any question? You can also either talk or write on the chat. No more questions? So, Julia, what do you think will be the next steps in this topic?
Well, maybe the first guess is to try to add more summands, like not trinomials but quaternomials. But it is much more difficult. So it is not like just one step. It is some more difficult task. Also, we can consider complexity not one but two, but this is also a difficult step. So something changes very to very hard. But I think that all these tasks are very intriguing, and one can think about them.
Okay, thank you. So if there is no more questions, I would like to thank Julia for her very nice talk, and
thank you.
The session of this, well, I'm going to say afternoon session, because for me it's the afternoon. I don't know wherever you are around the world. Well, anyway, I hope you have enjoyed this talk, and let's see you next Monday. Thank you.